Welcome students for the solution analysis video of your homework 2 in digital communications. So in your homework 2 you had 4 questions, each carried 25 marks, and let me go through the detailed solutions for you. So in the first questions you are given two signal constellations, and the first part of the question asked you to justify that they have both the same probability of error. So if you look into the constellations carefully, you can see that between two signals, the distance is twice alpha. So it's pretty straightforward from the first constellation. So this one is plus alpha, this one is minus alpha. So the distance between these 2 points is 2 alpha. And in this case also you can see that the distance is 2 alpha between these two signals, and then in fact between any two signals, because if you um, sum this of the squares of these two distances, so this is uh, 2 alpha square plus 2 alpha square, which is 4 alpha squares, and if you take the square root, that is 2 alpha. So these two distances in both the constellations are same, and you know that the probability of error is only dependent between the distance between two signals in the constellation. So even if these two constellations look different, but both of them have four signals, and in both cases, if they have same a priori signal probabilities, then the probability of error will depend only on the distance between pairwise signals. So both these constellation have the same distance, therefore they will have the same probability of error. For the next part, for calculating the energies, so you see that um, the energy is given by the the energy of each point, which is basically the distance of the signal point from the origin of the coordinate system or the signal space, and then you divide by the number of signals. So for the first constellation you have the energy, so each point is at a distance, alpha square plus alpha square, so that is 2 alpha square, and you sum them up, divide by 4, that is 2 alpha square. And for the second constellation, if you see, this signal is at origin, so the distance from this signal to origin is 0. This signal is has the coordinates square root of 2 alpha, square root of 2 alpha, so the distance is 2 alpha square plus 2 alpha square, which is 4 alpha square. This one is at a distance 2 root 2 alpha from the origin. This is all along the phi 1 axis, so this is again 4 times 2, so 8 alpha square if you square this, and then this one is also at 4 alpha square. So if you sum them up, 0 plus 4 alpha square plus 8 alpha square plus 4 alpha square, which is 16 alpha square, and if you divide by 4, then it is 4 alpha square. Some of you got this wrong, so some of you got this as 3 alpha square, and that was wrong, so you lost some marks there. um, but overall most of you got this question right. The justification on why the probability of error is same was more or less right, and then these calculations were also all right. Some of you got this 4 alpha square as 3 alpha square, so you lost some marks there. And the main thing about this is the explanation. So if the explanation was not perfectly all right, so I deducted some marks, but otherwise you did well, all of you did well on this question. So let me move on. So for question 2, again you had this 9qm constellation, and the first thing is that you are asked to compute the probability of error in terms of q, theta and l where Q is the probability of error between these two signals S1 and S2, which is D apart. So that's the probability of error for these two signals. And if you have now 9 signals like this which are all D apart, then what will be the probability of error of this constellation? That's what you had to compute. So first thing is that the probability of error doesn't depend on translation and rotation of the axis. So this this theta and L, this won't come into the probability of error expression. So it's independent of the rotation and translation of constellations. So this was actually analyzed in the class. So if you go back and see the lecture notes, you will see that this is indeed the case. So the probability of error will only depend on Q. So the final probability of error that you will be computing will be a function of Q only. And if you look carefully into the constellation, so this is like 9QAM, and each of the signal points actually are part of two independent ASKs actually. So basically the 9QM is the combination of three independent 3 ASKs. You can write the probability of error of 9QM as 1 minus probability of being correct for a 9QM. So this is basically 1 minus probability that each signal point on the 9QM constellation is correctly received. So what is that thing? So 1 minus probability that each signal point on the 9QM constellation is correct because of each arm of the two independent perpendicular 3 ASKs of which it is a part of. So if you see, so this signal is a part of this 3 ASK and this 3 ASK. So basically this is there are two 3 ASK here. One is in this side and the other is perpendicular here, and these two are independent. Again, this signal is a part of this 3 ASK and this 3 ASK. So if you see, each signal is actually a part of two arms of two 3 ASKs. So that being said, the probability that each signal point on the 9QM constellation is correct because of each arm of the two independent perpendicular 3 ASKs of which it is a part of. So basically these two are independent. So this is basically the multiplication of these two probabilities of being correct. And what are those? Those are 1 minus the probability of error of those 3 ASKs. So if you use this logic, then you can see that probability of error for a 3 ASK is given by this formula for M. So if you see your lecture notes, you will see for an M ASK signal the probability of error is this, where this Q is actually the Q function. So if you replace M with 3 here, you will find out that this particular terms P3 ASKs are 4/3 Q. So if you replace them in this expression, you will get the final expression of the probability of error for the 9QM constellation. So basically, again, the logic I repeat. So each of this signal on the 9QM is actually part of two perpendicular 3 ASKs. Okay, so the probability of this signal being correct is the multiplication of the individual probabilities of these three ASKs being correct, which is again 1 minus the probability of error of these three ASKs. So that's why this 1 minus p 3 ASK terms comes twice, and then the whole thing is the probability of being correct for the 9QM constellation, and if you are deducting that from 1, this gives you the probability of error for the 9QM. So that's what the final expression is. Now if you use union bound, this is easy. So you just use the formula for union bound. You will find that the probability is upper bounded by 8 third q, and for nearest neighbor the probability is upper bounded by 2q, and you can see easily that the exact probability that we calculated here is lowest, and then these upper bounds will come. So first will be the nearest neighbor and then the union bound. So that's it for the second question. And again, most of you got different parts of it correctly. So some of you didn't do both the union bounds and nearest neighbor. Some of you just did the union bound calculations and compared with the exact expression. uh, so those of you who did all three probability calculations and then use this comparison uh, got the maximum marks on this question. Otherwise I had to deduct accordingly, so depending on your calculations and also the explanations of the calculations. Then comes question 3. So question 3, you had two FSK signals and you were asked that show that the maximum Euclidean distance between the two signal vectors S1 and S2 occurs when the dot product is minimized. So that was part A. So for this part, many of you tried to solve it in different ways, but I think you got the concept right, but then the implementation was a bit roundabout. So all you need to do is just to write down the expression for the Euclidean distance, and you have this expression. So the first two terms are the norm of the signals, so those are the energy actually, and then this is the cross product term, and all you have to write is that if you minimize this term, because this is the term that is getting deducted from these two constant terms, so if you minimize this term, then the Euclidean distance will be maximized. So basically you have to write that this is maximized when S1 S2 is minimized with the proper logic. But most of you did a lot of calculations and then actually used the the dot product in terms of the cosines, and then the value of theta was found out for the cosine function to be minimum. All these things were not required. This is just a simple exercise. So but you still obtain marks for getting the concept right actually. So this part was okay. For the next part, what happened is that yeah, you had to do this calculation. So for the next part actually you had to calculate the dot product based on the signal values that were given, and then you will have this expression, and the minimum of this is basically obtained by differentiating this function and setting it to 0. So this would yield you an equation tan y equal to y, where your y is this 2 pi delta ft, and the least value occurs when y is 4.49. So basically your delta f 2 pi t is 4.49, so therefore your delta f is 0.715 t, and therefore the distance between the signal vectors is again s1 minus s2 square, so the norm, and that is actually this quantity times the energy, and the corresponding probability of error is calculated based on this distance, so this comes to this value. So some of you didn't calculate the probability of error, so you just stopped at this part, so that's why I had to deduct some marks for that, but most of you got this right also. So moving on with the fourth question, so most of you couldn't solve it, or didn't try to solve it. So this was solved by very few of you actually. So those of you solved this scored the maximum marks in this homework actually. So so the first part of this is sketch carefully the impulse response of the filter matched to ST. So if you see carefully, um, the impulse response of the filter ST is ht equal to s of capital T minus t, and your capital T here is 3 seconds. So if you put 3 minus t, and if you see the signal and if you shift it 3 places, it will be the same signal again. So basically your impulse response is just st, and you have to sketch st again. The output of the match filter again, so since your match filter is st, so this is st convolved with st, and then if you do the math here, you will get different values at different intervals. So this is a piecewise function, so uh, for different intervals of t, the values will be different, and then the final function will look like this. Then the next part was actually to calculate the output of the match filter for t small t equal to capital T, which is 3 seconds. So at the output of the match filter, the noise will be the n tau convolved with ht. So again your ht is basically st, so this is this thing, and then what you have is a simplified expression. So this is basically n tau times the signal s tau, and you integrate it from 0 to t. So so the variance of the noise is therefore is the expectation of these terms. So this is basically n tau. You are using two dummy variables here, tau and v. So n tau nv, s tau sv, and you are running this double integration. So and I'm doing this expectation, and if you do some adjustments here and some manipulations with the variables, you will see that this is basically s tau times sv times the delta function of tau minus v, and then you can carry out one of the integrals of this double integral. So then it will be, so this integral 0 to t sv delta tau minus v dv will give you s tau actually. So this comes to s squared tau delta tau, and then this is basically the energy of the signal, so that is a square. So basically you have n0 by 2 times this is basically 4a square, so the final expression will be n0 a square. And for the probability of error part, so it says that determine the probability of error as a function of a and n0. So this is actually an antipodal signaling scheme. So for antipodal signaling, you have the probability of error, which is this is basically the BPSK case, which is antipodal. So probability of error is this Q function of the signal to noise ratio, uh, where this is the output SNR from the matched filter. So you have signal power divided by the variance of the noise. Variance of the noise you already calculated, and this is the signal power part, and you have this expression for the probability of error. So this was the homework 2 for you. Part 4, or the question 4, was not solved by many of you. Some of you just solved the first two parts of question 4. Some of them just solved the first part. So accordingly I had to deduct marks. So this has 4 parts, therefore like 25 marks for 4 parts, so roughly 6.25 per part. So those of you did all 4 of this got the full marks for question 4. So that was homework 2 for you. Thank you very much.